who know me, yes, but for those who don't, I was here before during my first postdoc, and also at the CC that we had a few years ago. And now I came back just under 2 years ago, or a year and a half ago, with a permanent position there at the CC. So I'm happy to be back. I'm from Portugal, in case you cannot tell from my accent, and I studied over there, and I went to the States for my PhD, and now I'm here for good. Right, so today I decided to talk a bit about some work I've done recently about including nonlinear surface reactions in classical random walk particle tracking codes. Right? Now, so especially since I know that usually there's quite a few students that come to the seminars, I decided to include a short introduction to particle tracking, where it comes from, why we think it's interesting, and what we can do with it. And then, because it's relevant specifically for this talk, I'll discuss a bit about how boundary conditions can be translated to a particle tracking framework, let's say. And then I'll get to the meat of the talk, let's say, about the work I've done recently, which is how to use this, how to develop this kind of boundary condition in a Lagrangian sense for random walks that can handle complex nonlinear reactions with rates that are not linear. So, yeah, short bit of history to begin with. So the idea of random walk modeling comes from these observations in the 1800s of pollen particles moving in water under the microscope. And so this guy Brown, at least according to registered history, I think he was the first to remark on this phenomenon, at least. And what happens is that he saw that these pollen particles were moving in this jittery, apparently random way, and he didn't know why, right? So the reason for this is that the pollen particles are bouncing off water molecules, which are moving around because at finite temperature, things jiggle around, and this causes this random motion, and you don't see the water molecules because they're super tiny, right? So with the microscopes at this time, you couldn't see the water molecules, but you could see the pollen particles. So if you don't know, you may be surprised to hear that it was Einstein who did the first model for this, at least that's how history goes. And apparently independently, at 1 year later, von Smoluchowski, that's really hard for me to say, sorry if I butchered, also published a model, a related similar model for Brownian motion. In honor of Mr. Brown, it's called Brownian motion. And the idea of these models was to explain how this kind of random movement works when you have these random collisions with molecules. And in particular, you could make deterministic predictions about the way that the clouds of these particles spread. Yeah?
People online telling me that they cannot see the presentation.
Oh, okay, that's interesting. So, Martin, do you know what?
I don't know.
I'll take a break.
But we usually sometimes work is we go out and then we go in.
That sounds like you.
Where you have you. Yes. So the question is,
can we hear back from people online whether this reboot fixed the problem? But they can hear me, right?
Ah, yeah, for sure. Yeah.
Oh, it came back. Okay, very good. Reboot.
You can ask them. Someone.
No, they're muted, I think. So we have to use each other.
yeah. And is there some answer from the audience? We can also go.
Then they arrive.
Or send a message or say something.
You can ask. Not to separate them.
Not yet.
Not yet. Okay. Any other?
So they cannot see it?
What if?
Maybe you have to share the screen, maybe unshare and share the screen.
Of course.
Oh, you didn't share the screen. That's very explainable.
sorry, that's my fault. Sorry.
Maybe you share only the screen. And still to the beginning of it.
Can I just ask you, why is it so small?
Yeah.
Because I'm using 16:9 and that probably doesn't like it.
I don't know if it's a projector issue or. No?
But like you could refocus the projector and stuff.
Yes, it was.
Perfect. Thanks for the feedback. You speak already. So I was here, I think. Yeah, and I was just telling, I was one further. Yeah, there you go. So I was telling the story of how people discovered ground motion, how they started to model it. And actually, another fun bit of trivia that I think is interesting is, this is 1905. It's around the time of relativity, close to the development of quantum mechanics. But this was instrumental to convince scientists that matter is made of atoms. Which is quite late, right? Like I find it quite surprising. So yeah, anyway, that's just a bit of context. What's important here is that, for the presentation, is that this way of modeling Brownian motion in terms of these particles that move randomly with some Gaussian jumps, okay, so they have a certain probability of moving in a certain way. When you take collections of these particles, even though the individual particles move randomly, the distribution of where they are, which is essentially the concentration field, right, or related to the concentration field, is deterministic in the limit of large numbers of particles. So we can make deterministic predictions out of random things, using things like the central limit theorem and whatnot. Now, for this particular talk, what I'm interested in is how we use this kind of random description to simulate transport of a solid, for example. Okay? And the idea is the same, right? Since we know that in the limit of large numbers of particles we have a deterministic concentration field, we could use this idea of moving particles around to simulate even classical problems that we usually do in a grid, in an Eulerian system. Right? So let's talk a bit about discretization, just to give you the context for how particle tracking works. So that thing over there is the advection-dispersion equation. I think at least most of you are familiar with it, but anyway, what it's saying is the change in concentration at a particular point in space happens due to advective fluxes in and out of the box, or of the point, if you like, in the continuum limit, and diffusive fluxes in and out of the point as well, right? So, if you're not familiar with the details, I guess they don't matter too much for the talk, but let's see how we usually discretize this, right? Like, let's think in one dimension, one spatial dimension, just because it's easier. In 2 and 3D, it's the same principle. So what we do is we can think of little boxes around the points where we are looking at the continuum description. And then we can ask, by discretizing also time, what is the change in concentrations over a time step at one of these little boxes? So, I mean, the physical idea is what I just told you, but the math is also quite simple, right? Like what we are doing is just taking discretizations of the derivatives, okay? You can discretize them however you like. I chose backward derivative here, just because I think it's easy to understand. So this stuff is saying that we lose concentration or mass at the cell because there's an advective flux taking it away. But we also gain advective flux from that cell, so that's why that guy is positive and that guy is negative. Right? You can discretize it in different ways, but the idea is always the same. And then you get a coefficient in front that tells you kind of like the strength of advection, of this movement due to advection, which connects a temporal and a spatial scale. So basically this thing, this thing is telling you that advection occurs over a characteristic length that's given by delta x over is v over delta t. Then we do the same thing for the diffusive flux. Here I chose a central derivative just because I think it's visual. The idea is the same, but now we have that diffusion homogenizes the characteristic length delta x equals square root of 2d delta t. So we have a square root here, which goes back to the whole Einstein description of this random process. Now the cool thing is, I mean, this is the basis of how we usually do Eulerian simulations. We discretize our PDE, our partial differential equation, in space and in time, and then we just move forward in time with even directly just using this kind of so-called Euler scheme. There's more complicated versions, but the fundamentals are there. Now, what this is saying, basically, if you interpret it in this way that I was discussing, is that you can also think of trajectories of particles, a la Einstein, if you like, a la Brownian motion, and they will move v delta t, right, of spatial distance over a given time step, and then they will move characteristic size of square root 2d delta t, but multiplied by this random term. Now, if we look at this here, we can just interpret this as weights of probabilities, right? Like you lose the mass in a certain cell because it has a 1/2 probability of going left or a 1/2 probability of going right, okay? But the thing is, we can also just put a Gaussian here because we know from the central limit theorem that if we take many steps, it's the same thing, as long as we choose the variance and the mean. So you can take a unit Gaussian here, 0 mean, unit variance, and then multiply it by the appropriate size that comes from the theory of how these stochastic processes work. And then glossing over the details of how we formally prove that, I think it's intuitive that if you look at large collections of these particles, you're going to get the concentration field back in the sense that I was discussing. So that's my quick introduction to particle tracking, and this is the fundamental formula, if you like, of how to discretize transport or advective-diffusive transport in a Lagrangian sense. You take your collection of particles that represent pieces of the mass, they don't have to be actual physical particles, right? And then the smaller your delta t and the more particles you put, the more resolution you're going to get, just like the finer the delta x and the finer the delta t, the more resolution you get in a classical solution. Okay, so why do we care about this? Well, first, because it's kind of interesting, right? It comes from a physical perspective that gives us some insights into how these processes work. But also because in numerical terms, this kind of approach has some benefits over Eulerian methods. Eulerian methods are better at certain things, Lagrangian methods are better at others. So this is an example from a paper where I'm a co-author back from 2017, where we did some comparisons of classical Eulerian and some of these Lagrangian approaches for fluid-fluid reactions, so reactions where two components are in the bulk, a bit to understand what are the benefits of these two. I don't want to get into too much detail in that, but basically the idea is that you inject basically two lines of particles, here I'm showing one, or two thin strips, one of a certain component A, one of a certain component B, you let them go, you let them react. And then you compare Eulerian and Lagrangian approaches, right? So what happens is that if you use sort of naive Eulerian methods, a bit like I was showing you before, you run into a lot of stability problems, especially when you have high vector number, when you have high velocities. And you also get, conversely, a lot of, to make your problem stable, sometimes you need numerical diffusion. So you get this fake diffusion that just comes from your numerical method and makes it in particular really hard to resolve reaction fronts where the reactive action is happening. So this can lead to significant overestimations of reaction rates for it. It is true, though, it should be recognized that there are other Eulerian methods that deal with these problems in different ways. They tend to be quite expensive, but they do work. On the other hand, when you're using Lagrangian simulations, which is what is shown in these two cases, this is over a few realizations, this is for a single realization, you get quite a bit of resolution in the front more easily, but you can get quite a bit of noise also inside your solution, so you may get many particles. But the bottom line is that, especially when you have these kind of front problems, where you don't have stuff all over your domain, you're just sort of concentrating your computational resources in the place where you need them, right? So that's cool. I mean, I'm not claiming that Lagrangian methods are the solution, the panacea for everything, but they do have their uses. Besides, they're cool. Now, this was for a bulk kind of reaction, right? We know a bit less about how to do surface reactions, especially at the pore scale, when you're using this kind of method. This is a Darcy scale simulation, so continuum simulation, but in at least some of the work that I do, I'm interested in resolving the pore scale, right? And I like I said, I like Lagrangian methods, so, and they're useful for the kind of work that I do. So I was interested in having some kind of method such that we can use this type of description to describe complicated surface processes, processes that involve an interaction between some component that is dissolved, or some components that are dissolved, and some component or components that are just attached to the surface. Could be the mineral surface itself, maybe it could be a biofilm. So you can think of many biogeochemical processes in natural media from, again, quartz dissolution, calcite deposition of dissolution, precipitation dissolution, biological processes, formation of biofilm, etc. So to deal with these processes at the pore scale, we need to think about how to deal with boundary conditions in this type of method, right? So we know pretty well how to do some of that. So here's a little sketch. You have your grains in your medium, but it could be whatever medium, 3D, 2D, rock structure, doesn't really matter, it's just a sketch. Our dissolved components are moving in the fluid phase, which in this case saturates the pore space. And then somewhere at the solid wall, we want to describe different boundary conditions, different processes. So, reflecting boundary conditions, you probably know that in the PDE sense, in the Eulerian sense, they correspond to zero derivative of your concentration field. So it turns out that there's a very intuitive version of this in terms of particles. If you make your particles collide elastically with the interface, then when you look at your concentration field, this is what you get back. You can prove that, but it's also intuitive, I think. You're basically saying nothing goes in and the surface is not really doing anything except bouncing. It's not wasting your energy, it's nothing. So we know how to do that. By the way, I didn't say like the n here is just normal to the surface. Here it doesn't matter because it's zero, but I'm making it point into the solid for this particular term. So the n dot grad is just the derivative, the concentration gradient, in the direction of the solid. If we have absorbing boundary conditions, again, as you probably know in an Eulerian sense, that means that we set the concentration to zero at the wall, because anything that touches there just gets eaten, right? And we can implement them by removing the particle if we consider like permanent absorption. We can also do adsorption in the sense that we can have our particles stick in here for a certain amount of time and then release them back. So we know how to do that. And then we also do know how to do linear surface reactions. Okay, so linear surface reactions, it's a bit less obvious perhaps, they correspond to Robin boundary conditions. Oh shoot, there's a C missing here, it should be minus kappa C. That's why it's linear, so we're saying this side we have the reaction rate, and intuitively speaking we're saying that it is the diffusive flux into the wall that allows for reaction to happen. And it happens at a certain rate. But more on that in a moment. So, anything else I want to say here? So this kind of thing is harder to do in a Lagrangian sense. There are a few options of how to implement it, but we can basically exploit the linearity of the reaction. The linearity of the reaction means, in physical terms, that the particles don't talk to each other. They don't know if there's a lot of particles around or just one, right? So we can individually look at the particles and compute the probability or the rate at which they are absorbed. So there's some work in the literature. You can use the first order description like that. There's also some higher order corrections that you can include. And this thing is telling you, so we're basically doing an elastic deflection, just like here. But then we eat some of the mass according to the probability that it reacts on contact. And using this kind of expression ensures that you get this back in the limit of many particles and small delta t. More on that in a second. You may be surprised about the square root delta T. That has to do with the funny way that diffusion works. The things grow like square root delta T, and it turns out that the number of hits of a nearby particle to the wall in a small time step behaves in a funny way for ground motion. Then you get a delta T. I'll show you a bit more detail on that in a second. So now, what we want to do, basically, what this work was about, was say, okay, we know how to do the linear reaction, but how do we generalize that so that we can do multiple reactions that can be nonlinear on the local concentrations at the surface, including maybe variability of solid phase reactants. Things. So we now have, any number of mobile species that are being transported by advection-diffusion in the fluid phase. And then we have a bunch of immobile species that are stuck to the wall, and they can have any set of reactions between them with whatever rate law that you want. So remember I said just before that we could exploit the linearity so that we didn't need to know about the local concentrations and the role of the other particles. Somehow now we have to know how many particles are around so that we know the concentrations. Right? So you could just go and reconstruct your whole concentration field and use that, but that's expensive and inelegant if you ask me, because these things don't need the reconstruction. So the question is, can we make some kind of collision-based estimation of these concentrations at the wall so that we can do the same kind of approaches for the linear case? Turns out that the answer is yes. So again, in the pore space, we now have a bunch of species, but they don't really talk to each other in the pore space. They just move by advection diffusion, just like before. Now we have these things that look like Robin boundary conditions, but instead of having a linear reaction here, we have some arbitrary function of concentrations, surface concentrations, and if you really want to, time as well. Doesn't really bother. This is from a conceptual standpoint. Now, just to explain this thing here, so even I get confused by whether the sign should be where it's easy to get the end the wrong way, and then you're not sure which way the flux is going. So I think it's useful to get an intuition for what this thing is doing. So this thing is setting the diffusive flux into the surface according to how much reaction you have there, and whether you're producing or consuming, right? So if you have no reaction, so if this thing is zero, you might recognize this as our old friend reflective boundary condition. Makes sense. It's like I said, we basically just reflecting particles. If they don't lose mass, we're back in the reflecting boundary condition. So your concentration field near a wall, which here I'm zooming in so it looks flat, okay? Is the concentration field itself will be flat near the bottom, right? Good old reflecting boundary conditions. When you have production, what you're going to do is you're going to increase the concentration near the wall because you're producing stuff there. So in the end, what that generalized Robin boundary condition is doing is producing this kind of gradient that is positive towards the wall. Okay, so that's why I believe the signs are right. If you have consumption, it's the opposite, right? Like you're going to have less mass near the wall because you're eating it. So you can think that your mass flux into the wall is being partially consumed. You have effectively a flux into the wall at this point. If you have instantaneous decay, you can put instantaneous decay here. How to do that? So, okay, you can take a linear reaction, like before, but now I remember to write the C. Okay, so kappa C. And then if you take the limit of the rate goes to minus infinity, you have a linear reaction that goes instantaneously fast. There's some detail maybe to the calculation, but basically intuitively what happens is the kappa becomes infinite, but we cannot have the gradient be infinite because that's a problem for our PD of diffusion. So it's somewhat intuitive, I guess, that C must go to zero in some way. That is what it is. So what happens in this limit is that this thing turns into an absorbing boundary condition, and we recover our C equals zero at the wall, well-known case. Okay, so how do we put this into our particle trajectory? It looks fancy, but it's really not that complicated. So I'll walk you through the little derivation because I think it gives some intuition. So basically what we do is we're going to estimate the mass flux that's trying to go into the wall before we remember that there's a boundary condition there, right? So as I said, if you zoom in, this thing looks flat, right? At least that's a reasonable assumption for reasonably behaved surfaces. And what we do is we look at the diffusive flux. This thing here is just, you know, the Gaussian kernel that looks at a particle trying to diffuse into the wall. But then we have to weigh our diffusive flux with the concentration field that we actually have near the wall. Okay? That's what this term is doing. So y is the position of the wall, and then we have like a small deviation from the wall. So minus sign because by convention I put the unit normal into the solid. Then there's two integrals here, right? Okay, so first there's this delta here. The 2 just comes from the way that you define these integrals. It's not really important for the intuition, I think. And the delta A tells you just, you discretize your surface locally, the more surface you have, the more stuff is hitting. So then there's two integrals, right? Like one is, as I was trying to explain, the initial condition. That's going into the when you're starting to get your mass. And then the second one is integrating over the positions that would have ended inside the wall. So those positions that would have ended inside the wall are the stuff that's hitting the wall during your time step. That's it. Okay, so now what we do is we tell and expand this little thing. We say if we have a small time step, the sizes of our particle jumps are going to be small. They're on the order of square root 2d delta t. So let's assume we have a small enough time step and expand this calculation of the flux near the wall. By the way, I didn't say, I don't know if anybody's confused why I'm not accounting for advection here. It's because near walls, you don't get advection into walls, right? That's why you don't need to worry about it locally. This is a Taylor expansion. The only trick here is that for the derivative, you use the boundary condition. That's how the reaction rates come in. So then, you solve those integrals and you plug this guy in, you solve the integrals that come out, and what you get is this nice relationship between the mass flux that's trying to go into the wall that you can get from your simulation when you're moving your particles around, and the concentrations that you want to know at the wall, that you need to know to calculate your rates, right? And there's an extra term that has to do with the reaction rate, which comes from the boundary condition. So now, you can solve this numerically to get the concentration, but it turns out that in practical terms, it's often enough. This term is higher order because of the square root delta t here and delta t there. So you can get a quick, easy estimate of the concentrations from the particles that are hitting the wall that you know from your simulation, using just that part and inverting it for slinger. Right? So that's really important for the method because it tells you, I have my mass fluxes that I get, again, directly from my particles moving around, my usual random Hall particle tracking simulation. I know what the concentration should be. Mind you, it's not that obvious, right? Like it goes like 1 over square root delta t. That has to do with the funny way that diffusion behaves. Remember the probability of hitting the wall that I talked about before? In the original paper, they also use a formulation like this, but they don't allow the concentrations to... They don't care about the concentrations varying, right? You don't need to get the concentration at the interface because it's linear. So then what you do is you say, okay, but I want to get my reaction rate right. So for over my mass flux, I define a reaction rate in the usual way of defining reaction rates in terms of what the boundary conditions should be doing. And I say that's the same for everybody. You put everything together and you get an expression for the effective integrated over the time step reaction rate for a given particle directly in terms of these rates that are just the actual rate divided by Ci, it's just convenient. So it's the rate that goes into the boundary condition divided by the actual concentration there. But of course, these things depend on the concentrations, but you can get your concentrations from your fluxes that you know from your usual particle tracking simulation. That's it, that's all there is to it. Now with this, you can get, now this is the cool thing, right? Like you can get from this, from single particle collisions, an estimate of the local concentration. So the problem is nonlinear. You need to care about all the particles that hit the surface, but you can look at them one by one. Because the flux is linear in the particles. Right? That's the basic idea. And then you can, I'm not going to get into detail because of time, but you can get sort of intuitive discretization criteria that you need to use for these things to give you good results, a bit like your Courant number and your grid-Peclet number in our simulation. So you have a criterion for delta T that you get directly from the rate. So the rate integrated over the time step cannot have this term too big because otherwise this would be even unphysical. You can even think of this as a probability, as I was saying before. Then you need enough particles to resolve your support volume for your description of diffusion, which goes like that square root to the delta T here, and then you raise it to the dimension of the space to get a volume, right? And V there is just like some reference volume, okay? Maybe it's the whole domain or the region where you have plume. And then you also need an extra thing for this kind of description. You need enough collisions where the reactions can happen so that you can estimate these concentrations right. So once you have fixed delta T, you could do it another way. Once you have fixed delta T and the number of particles, what you can do is make sure that your discretization of the area at the wall is not too small. Because otherwise, not enough particles are going to hit it, because you haven't put enough particles. So there's some sort of semi-heuristic arguments that you can make to estimate the number of collisions based on the previous description, and you get a criterion like that. Okay? And now you have your algorithm, right? Like you update your particle positions using the usual random walk formulation. Then you check who hit walls. You reflect them as needed as before, elastically, and you remember who hit where, okay? Then you go check the places where particles hit, and you use the previous formulation that I was just quickly deriving for you to compute the surface concentrations of the mobile components. You know your solid concentrations. You compute these integrated over time rates from the previous description, and then you just update particle masses in the usual way, okay? The usual way is that thing over there. Actually, I'm pretty sure that delta T shouldn't be there, so sorry about that. And then you do the same for the solid components that are changing at the surface. Okay? But for the solid components, you basically just have an ODE locally. For each discretized region, you just have the changing time directly, as long as you know all these other concentrations. Example, so I just took, to verify this, I first did no advection, just pure diffusion in the square. And then at the walls of the square, I chose some nonlinear reactions with multiple components, including one solid component and two fluid phase components, these are components. And you can write the usual Eulerian Robin-style boundary conditions for this thing. It's just like rate equations for the change. And as you can see, so you have the usual Robin, and then you have, I mean, it's a partial derivative because you have one for each location on the boundary, but you have essentially an ODE for the solid phase. And then you discretize the sides of the square however you like. Remember, we don't need to discretize the inside. That's the nice thing about this. You do need to discretize the wall, because otherwise how do you even know where particles hit? Right? And then you use these criteria from before, so these you just choose some proportionality constants to decide how much precision you want, basically, or to estimate the precision you want. And you can check, so for this, I chose this system because in some limit it looks like a lot of Autor. So like what predator-prey models do. So I knew that in some regimes it would do oscillations, and I just thought that was a cool example. And also in the limit of slow reactions, you can reduce the whole thing to an ODE for the masses, to ordinary differential equation for the masses, and then you integrate that with your favorite ODE integrator. It's just a time integration, basically. That's why I say semi-analytic, and you find that it works. It does the job. It fits the. It gets the right masses. This is the total mass of the different species over time. There's some asterisks. They're just reasonable non-dimensionalizations. In particular, for time, it's the diffusion time that I'm non-dimensionalizing. And mass is just initial mass. And then it also converges in a reasonable way, right? So for the arbitrary down-color number, we don't have an analytical solution for that or anything like that, but we can still simulate it. And then check how the error is going down by looking at a very result simulation, which we now believe is doing the right thing because it was doing the right thing in this case. And we check how the error is going down towards the very result simulation. So we can make some theoretical arguments on why these things should be linear in delta t for the error. We do find that when the time step is quite small compared to the diffusion time. These Lagrangian methods, in my experience, they tend to behave a little bit more irregularly for relatively big time steps when compared to the Eulerian codes, one of the prices we pay. My explanation for this is that this has to do with the fact that when we make our semi-heuristic estimates of the errors, we assume regions when we have well-mixed particles. And in practice, that's not true. So I think this is why you need a very small time step to get this. I'm also showing here, by the way, so these are different down colors in different colors. The squares and the triangles are explicit and implicit for the local reaction system. So it turns out that even though the movement is unconditionally stable just because of how you do particle tracking, like there's nowhere that this thing can blow up, it's just particles moving around. But for the local reaction system, you're basically solving some ODEs, so you have the usual problems of stability or not. So it turns out that for high down color, if you don't take a sufficiently small time step as you would expect, you start getting divergences. You can get rid of those, or at least mitigate them, by using your favorite implicit description near the wall. I use the Newton-Raphson scheme I made it first. That's basically one of the reviewers first. And then just very quickly a more fun example. So just a single reaction inspired by calcite dissolution. You have two regimes, both power law rates. One is almost linear, far from equilibrium. Another one is strongly nonlinear when you approach equilibrium. I got the parameters from this paper here. I made this synthetic porous medium by just throwing some grains in there, some circular grains in 2D in there, jiggling them around for things to be a bit more fun. I solved the flow, and then I did using OpenFOAM, if I remember right, and then I did some particle tracking on top of that using this and this sort of simplified calcite dissolution reaction at the grains. The grains don't change size here; it's quite a simplified problem. Okay? But basically, so you can use these ideas from random walk particle tracking to just describe the front, so you describe the deviation from equilibrium and you see how it evolves. And I don't have a solution for this, but you do get convergence in terms of particle numbers. Naive arguments give you n to the minus 1/2. You get, in practice, I found something between convergence with 1/n and n to the minus 1/2. Again, I think it's because the particles don't stay well mixed, so it's hard to make a good, precise estimate of how the error goes down. And I tried looking at different Becker numbers, and you find, you can use this to look at the different behaviors of the mass, and you can see that you get, decent convergence properties with n. Since it's getting late, I won't go into the physics too much, but I just wanted to say that it does look like it works when you have heterogeneous velocity fields. So I'm going to end now, but this is just a fun little video that I made a while back where we have a linear reaction where we don't have a saturated domain, we have also the presence of air bubbles that are static. This is extracted from the experiments of my friend and collaborator Oshri. And I just did some preliminary simulations using this code I've been developing that basically combines particle tracking ideas of this kind with my own code and some OpenFOAM functionality in the backend with the OpenFOAM backend. So the idea is to be able to get your Eulerian solutions for the fields from OpenFOAM and then do these kinds of use these kinds of algorithms to do part scale simulations using particle tracking. So that's work in progress. We're also looking at moving phases. It's just to show you a cute little video and to say that there's all sorts of fun stuff that you can do with this if you feel like it. So again, like you can get statistics over particles, you can get mass decay as usual, you can get breakthrough curves by looking at how particles cross on the other side, whatever you feel like. But again, so this, I have not implemented the nonlinear stuff here, this is just a linear relation. Okay, so basically I've discussed the new way to do nonlinear coupled surface reactions using classical random walk particle tracking. If you're interested in the details, the paper came out quite recently. And there's also a little Zenodo repository where I put the code. It's not super polished, this particular code. And this one does not have the connection to OpenFOAM. The fields were simple enough that I just came up with my own collision detection, if I remember correctly. I don't think I used OpenFOAM. I did for the field, for the velocity. The other case, sorry for being a bit rambling, but the other case with OpenFOAM, I do have a GitHub repository, I'm working with other people, but it's not quite public yet. I hope it will be soon. So again, this method allows you to estimate these concentrations and reaction rates just from sort of summing over single particle collisions. So you don't need to discretize the bulk as usual for random walk particle tracking methods. You do need to discretize the surface though. You don't need to reconstruct the concentration fields like at every step. You can do it if you want to look at it, but it's not part of the insides of the algorithm. And you don't need to go around looking for pairs of particles or sets of particles which can be computationally distinct. And because you have this sort of linear way of summing over particles, even though you get a nonlinear effect from looking at the concentrations, this has some benefits or it gives you some new ideas on how you could go about parallelizing these things. So I tried in a simple way, you can parallelize sort of over particles and over places where they hit. There's some details to that, but it's not so hard to do, at least at preliminary implementation. I tried on a meter, like 4 cores on my own laptop, and it's not quite a linear increase in speed because there's some interaction, but it looks promising enough. And yeah, that was my story for you today. So, thanks for your attention.
Questions or comments?
Yeah, very interesting. I mean, I got the idea. Can you make the particles grow or shrink according to precipitation or so?
You mean the solid particles
Yes,
or
the solid particles.
Yeah, okay, so I've definitely been thinking about that. You definitely conceptually can. You have the usual issues because that's going to impact the flow if you're serious about it. So you don't get the benefit of having your flow already solved and then doing this on top. So you'd have to have a coupling between the two. Right? And then there's one more thing that is a bit problematic. So you need some way. It's definitely possible to do, but you need some way of, especially for precipitation, of dealing with situations where you have a particle here that just hit, and then you get that position, this thing grows, and your particle suddenly is inside if you don't have sufficiently small time step. So that's been around in my head. You need some way of dealing with this. Yes, it goes away, it should go away in the limit of small time step, but you have to be.
You have to be moving this boundary condition. We are not fixed in space anymore.
Yeah, so there's nothing fundamentally problematic with that for the method, but in practice, it's not trivial to implement. So I hope I can do something like that in the future. It's in my head.
When you go to slide 12, you have some basic questions to understand the tools modification.
Cool, no problem.
So,
I will do it faster.
so this is, the first plots you have with the sinusoidal It's literally at the boundary.
No, so this is, okay, I did go a bit fast here this time. So this is just the total mass of, these two are the mobile species,
Okay.
and this is the total mass at the wall. There's a net there because of how I define my square and my non-dimensionalization. So that's just the time evolution of the total amount of mass. So when you integrate your concentration fields over either the bulk or the wall, depending on the case, that's what comes up.
But in your case, you only get the concentration from this method, not with the Eulerian method. You only get it, I mean, the mass of the solid or of the two other fluids in the border of the.
No, okay, so while you are running your method, you need to compute these concentrations at the wall so you can compute your reaction rates, which you do in this funny collision. That's one thing. The other thing is, you still know where your particles are inside the box.
You use the discretization you use.
Yeah, so you could rebuild the concentration field, but to compute total masses, you don't have to. You just sum you just sum the masses of each particle over all particles.
Okay.
That's it. That's one of the reasons for looking at mass.
So in general, so it's really the mass.
Yeah, the total mass in the box of each thing, basically, or on the walls. So that's one of the things, right? Like getting total masses is really easy with Lagrangian methods. Getting good resolution on concentrations can be more challenging. You might need more particles. So depending on what you're doing, you might be better off with the Eulerian or Lagrangian. And this here is the error in the masses, looking at a fine comparing to a fine simulation. And it's the average over all the components or all the mobile components, I don't remember right now. But it's more or less the qualitative behavior, it was the same, I think, for all of the masses, if I remember.
It should be linear, you say.
So that just comes from, like, if you go back to the derivation and look at how the errors behave and what you are neglecting,
Okay.
what order you are neglecting things at,
Okay.
you make some arguments by considering some kind of well-mixed volume for particles or something like this. That's usually how you go about it. And then from there, with some formality and a slight bit of hand waving, you get a delta T behavior. And it seems to be consistent with what I see. That's it. Okay. Yeah.
Go ahead.
In your opinion, do you have any ideas how we might prove the algorithm for larger delta T?
For larger delta T?
Yes.
So I'm not sure if I understood, but if I go.
If I want to use the same algorithm I've been trying to do that with the same expression of the Autor expression.
Okay.
And I would have a problem with large delta T's, large Groundwater numbers, let's say.
For last time, yes, okay. So what happens is, if you have a very high
Do you have
value.
any ideas or something?
Yeah, so one of the things is, so first, there's no free lunches, right? Like, you either resolve your process or you don't, and, it's like if you have an Eulerian grid with delta x that is this big, and your physics happens at this scale, you're not going to see it, that's it. Right? On the other hand, sometimes the small stuff doesn't do that much, and your problem is that you're going unstable. So maybe you're not resolving all the processes, but if you can keep it stable, you might get a decent
So
solution.
here we get a probability that's larger than 1.
Yeah, that's because, so I gave the special example because it's easier, I think, to
Yes.
understand. But for time, it's the same, right? Like, you're just not resolving things that are happening at the small scale. So you do have a few options there.
Okay.
One thing is you just hope that that doesn't matter so much, and you just try to maintain stability, and you do that by, I don't know, cutting off the probability at 1, and then if you have nonlinear reactions, maybe using an implicit method for the reactions at the wall.
Okay.
That's an option. A better option that's, for many cases, that's actually simpler, is to just say, look, if the reaction is that fast, if it's fast compared to diffusion, then it's instantaneous. Right? So there's two things here. You could be fast compared to your time step because you just don't have the computational power, so who knows? But you could be really fast compared to all the other processes, like diffusion. So if that's the case, what you can do is every time a particle hits, it just dies. Instantaneous reaction, that's it. So that's another option.
And the other question is, does this work for 3D?
Oh, in principle, absolutely. In practice, depends on the problem whether you might need too many reactions and sorry, too many particles
Yes.
to get good resolution. So I haven't done that with this. And what I can tell you from experience with these things is, if you have a problem where there's stuff everywhere, you're probably better off using an Eulerian method. If you have a problem where you're trying to resolve a front and then it may be advantageous to go Lagrangian, because you're not wasting resources everywhere and you're better at resolving the front. So that's my general advice. By the way, quickly, here, for example, like this thing is a reaction that tries to get you to equilibrium.
Okay.
So what we're looking at is, what's interesting is deviation from equilibrium, right? But, so if you start trying to look at calcite dissolved in the water directly, you're going to have the equilibrium calcite everywhere doing nothing. That's a waste of resources from a Lagrangian perspective, right? So what I did for this thing is I had the idea, okay, why don't we just think of the component, right, like that is the mass deviation from equilibrium. So then you look at how your equations behave for that, and you just have your particles transport the deviation from equilibrium. And then this becomes a proper front problem, and then it's probably a good idea to use Lagrangian. So sometimes you can be creative about it,
Yeah.
but if there's really stuff happening everywhere, especially in 3D, this is going to be interesting. Yeah.
Okay, thank you. Thank you.
Cheers. Yeah.
Few very basic questions.
Go for it.
Can you go back to the first test? Yeah, this.
Okay.
Well, one is more general. So, what is the reasoning behind the estimation of the minimum number of particles? This comes from some numerical analysis.
So now it's a semi-heuristic theoretical argument. So for this thing here, I'm basically saying if you have
Switching the light.
So
Switch on
basically,
the lights. Switch on the lights.
so basically, in each time step, each of your particles is going to come somewhere with a characteristic jump size square root to the delta t. Right? And the idea, which is similar to what you get on a grid, is that you want to have enough resolution inside here so that you're not blurring over things that you're not resolving. So that you're not resolving things temporally that you're not resolving spatially. It's a bit like when you have a Coulomb number and your time step is too small for your grid size. Right? So you need a bigger grid because you're trying to resolve temporally too much. Right? So you're basically, your particle is doing a lot of jumps, but in this whole region where you're doing a lot of jumps, there's nobody else. So you're not seeing this region properly. So but the argument is basically this. For this, it's a similar idea, but what you're trying to say is there's a delta A region here, and I want to estimate concentration. So within a time step, I should have enough particle hits that I can get a good estimate of concentration out of it. And the basics of the argument is just that the particles that are going to hit within a time step are particles that are more or less within this kind of diffusive distance from the wall, otherwise they don't hit. So then you try to make sure that you have enough particles there, and since the way I thought about it, you've already fixed delta t and you've already fixed m, what you can play with is just make this thing bigger if you need to, so that you catch more particles. And then it's always a bit heuristic because you always assume that over some support region you have the particles mixed everywhere. So if you have a plume, you can just think of the typical size of the plume and think of it as more or less well mixed there. So in practice, when you look at the convergence properties, they're not as clean as for Eulerian methods, and I think that's because there's this element of heuristicness going on. Does that help?
Yes, this takes me to the second question when you do the convergence.
Mm-hmm.
So I was surprised when I saw the convergence done with delta t. I was expecting more convergence with respect to delta r.
Yeah, okay. So I thought it was more interesting to use delta t because my idea. So in my experience with Lagrangian methods, it's often difficult to know the relationship between the numbers of particles and delta T's and whatnot that you have to put, and you end up with a bunch of loose discretization parameters. And sometimes it even diverges if you make your delta T too small, So what I wanted was a way to say, okay, you can just fix everything else so that the time step is what dominates your error. And that's why I decided to go with this. So what's happening is that, maybe I think I was not clear enough with that. What I do is, the number of particles and the area are not fixed for each delta T here. Right? So I'm applying those criteria with the constant in front, which is 10 Q. Okay? To make sure that, right, so this thing here is telling you the bigger you make n in comparison to this, the more resolution you proportionally have, let's say, inside that volume. The more you make this big compared to that, the more that gives you an estimate of how many collisions you're actually getting. So I'm doing 10 cube in each. Right? And so what that says is, as I reduce my time step, I make sure that everything else is sufficiently resolved such that I expect the bulk of my error to come from the time discretization.
Yeah,
that's why I do it.
So you not keep it constant, so you
Yeah.
change it.
Absolutely. That's really important.
And then,
Sorry.
yeah. And then, am I blind or is delta T first? It's a times in the plot. So times no in the right one. The convergence one. Is that the convergence one?
Yes, that guy.
No, the x-axis. Is that delta T first? Or am I blind?
Time step delta.
Time step delta T star.
Delta T star. So what's
The star is the non-dimensionalization with the diffusion
okay.
time. Okay. This I mentioned, but also very quickly. So this would be the diffusion time here. And so you can see that you need quite small, between 10 to the minus 2 and 10 to the minus 3 diffusion times to get the convergence rate that I would expect. That is actually what I'm used to seeing for these kinds of methods. You need, because this thing goes like square root, maybe that's not the reason here, but you do need a lot of resolution within the diffusion time to get concentrations right and reaction rates right. That's unfortunate, but it seems to be true. Yeah.
So what is the length scale?
Length scale.
Usually for diffusion time.
Yeah, it's half the size of the square. And that's the same thing I use for the down color. It's the same length scale. And here the down color was like 10 to the minus 2, I believe, and for one of the reactions it's twice because I wanted to be in the oscillatory region for fun.
Last question.
Yeah, you want to close one?
Yeah, Tomás, thanks for your wonderful report. I'm very interested in one thing, so what's the computational efficiency of your method that run more point tracking compared to the Eulerian method or the advection-diffusion?
That's a very good question, but also a hard question to answer. One thing is, the rate of convergence is important,
Yes.
and it's not an extraordinary rate of convergence, right? But that's typical of Lagrangian methods. And you have to keep in mind, as I was saying before, that this is not really fair because we're also putting more resolution as we in other things like number of particles as we reduce the time step. So as I was saying, so that's something that I have not looked at in enough detail to give you like a hard answer. But in my experience and also from the tests that I did for this particular method, this is good, or it's useful or potentially useful anyway, if you're looking at the reaction front. So if you have a small region where your reaction is concentrated and where you need a lot of resolution and you don't want to waste resources in the rest of the domain. In practice, I think that, at least for most cases, if you have a domain that's full of stuff happening everywhere, like, if you have dissolution everywhere along the domain, especially in 3D, I would say that you're probably better off using another inlet.
Okay, thank you.
I think anybody who tells you otherwise is lying to you. But I can do it.
Okay, I think we have to leave the room because there was so.
Thank you.